All right, let's jump right into this explainer and demystify the UVM driver. This is the critical and honestly often misunderstood bridge between your high-level abstraction and low-level hardware execution. If you've been working in functional verification for any amount of time, you know that creating those smart, randomized transactions is really only half the battle. The actual magic happens when those abstract software concepts get translated into physical, cycle-accurate electronic signals that stimulate your design under test, or DUT. So today, we're going to master exactly how that translation goes down.
Here's our roadmap for the explainer. We'll start with the driver's essential role, deconstruct its anatomy, break down the sequencer driver handshake mechanics, look at driving the actual DUT signals, understand component phasing and connections, and wrap up with debugging using TLM responses. Let's get to it.
The driver's essential role, or as I like to think of it, the ultimate translator.
High-level verification objects are practically useless if they can't talk to the hardware, right? To really grasp this, we have to contrast the two most tightly coupled components in your agent. The sequencer is the manager. It acts as an arbiter for abstract transactions, but it knows absolutely nothing about clocks or pins. The driver, on the other hand, is the active consumer. It's the worker on the front lines translating those abstract items into tangible, low-level stimulus.
The UVM Driver base class declaration is built for serious flexibility using a couple of key parameters: REQ for the request transaction and RSP for the response. Now, by default, RSP is the exact same type as REQ, but you can completely separate them if your specific protocol demands it. This clever design is what lets you build highly customized drivers while still inheriting UVM's standard communication infrastructure.
Moving right along to Section 2, Anatomy of the Driver. Let's deconstruct this component.
The absolute most crucial point to understand here is that the driver operates in pull mode. It actively requests work rather than sitting around waiting passively for data to be pushed to it. This is a defining characteristic of the UVM driver. It uses a specialized transaction-level modeling, or TLM port, called the seek item port. Think about it. Because hardware runs on continuous, unforgiving clock cycles, the driver has to dictate the pace. It decides when it's ready to wiggle the pins, and at that exact moment, it pulls the next transaction from the sequencer.
Looking at the structural hierarchy, you can trace exactly how that seek item port bridges the gap straight to the sequencer's export. The UVM seek item pull port on the driver side communicates directly with the pull export and implementation on the sequencer side. This unified channel makes the entire pull semantic possible. It's literally reaching out across the component hierarchy to grab the data it needs to drive the bus.
So how does it actually grab that data? That brings us to Section 3, Sequencer Driver Handshake Mechanics, pulling the data.
To make this handshake happen, the driver relies on specific interface methods to talk to the sequencer's FIFO, most notably get_next_item and item_done. When your driver is ready to do some work, it calls get_next_item. If an item is waiting there, it's passed down immediately. But if not, the thread just completely blocks until a sequence produces a new item. It's a highly synchronized dance.
This simple three-step loop is the absolute heartbeat of your driver component, and it typically lives inside a forever loop in the run phase. Step 1, block and wait by calling get_next_item. Step 2, execute the cycle-accurate pin wiggling, asserting addresses, shifting data, doing whatever your specific protocol requires. And finally, Step 3, and look, we've all caused a simulation to hang by forgetting this, you absolutely must call item_done. Calling item_done is mandatory because it officially unblocks the sequence and completely clears the processed item from the sequencer's FIFO. Until that call happens, the sequencer still considers the transaction active, and any wait for item_done calls in your sequence will just hang forever. You can also strategically use this call to pass a response object back up to the sequence if you need to return read data or a specific status.
Okay, Section 4, driving the DUT signals. We're going from transactions to actual physical pins.
This is where the abstract code finally becomes active, tangible electronic stimulus for your design under test. The driver takes the data payload from the object it just pulled, and it painstakingly maps it to a virtual interface connected to your DUT. This involves highly protocol-specific timing. It might mean waiting for a positive clock edge,
checking if a grant or ready signal is asserted by the DUT, driving an address onto a bus, and then pushing the data payload on subsequent cycles. In a practical implementation, you're usually splitting a single transaction into specific bus phases. The driver might accept a transaction, execute an address phase, maybe release a lock to allow for pipelining, and then execute a data phase. It is fully responsible for managing the temporal reality of the hardware, breaking a single instantaneous software object into multiple time-consuming states.
So, how do we wire all this up? Section 5. Component phasing and connections. Timing the integration.
UVM's strict phasing is exactly what ensures the driver is fully wired before it ever attempts to pull a transaction. The hierarchy is established top-down during the build phase. Then, and this is crucial, in the non-time-consuming connect phase, the TLM ports between the driver and sequencer are physically linked bottom-up. Only after every single thing is securely connected does the simulation launch the time-consuming run phase, where our three-step loop actually begins executing in parallel.
During that connect phase, there's one precise line of syntax that definitively links your driver to your sequencer, usually executed inside the UVM agent that encapsulates both components. This line calls the connect method on the driver's seek item port, passing in the sequencer's seek item export. Without this specific line, your driver is going to throw a fatal null pointer exception the very first time it tries to call getNextItem. Finally, Section 6. Debugging with TLM responses. Let's monitor that bus health.
Because when your driver interacts with a physical bus, things will inevitably go wrong. A slave might not respond, an address might be out of bounds, or a command might be unsupported. Instead of just printing a quick warning and moving on, a robust UVM driver captures these bus-level errors and encodes them into standardized TLM response fields before passing the transaction back to the sequencer.
By deliberately checking these specific TLM status flags after a transaction, your test bench can intelligently catch and debug precise physical interface failures. For instance, if your sequence pulls back at UVM_TLM_address_error response, your test can dynamically decide to gracefully recover, maybe by rerouting the packet, rather than just letting the whole simulation crash. It pushes that physical debug information right back up to the abstraction level where your test scenario is actually being managed.
Think about how mastering this handshake fundamentally shifts your ability to conquer hardware verification. The UVM driver isn't just some passive component. It dictates the timing, it controls the stimulus flow via its pull mechanism, and it actively reports on the physical health of the bus. By properly understanding its ports, its three-step execution loop, and its error handling capabilities, you can write much cleaner, much more reusable verification IPs. So the question is, how are you going to implement these strategies in your next project to build a truly bulletproof environment? Thanks so much for joining me on this explainer, and happy verifying.